Our second lecture for the streams section and the rivers and streams section is talking about the work of streams. So we're going to talk about how streams kind of carve out landscapes. So we discussed a drainage network the last time. We'll just talk about how drainage networks can be carved and specifically focus on meandering streams, which is what the picture is on this image or on the slide here. So same thing as before, simultaneously you'll be taking Streams Quiz 2 as you watch this lecture. Just to give you a couple examples from some national parks of where streams have carved out some beautiful landscapes. This is in Yellowstone National Park, Yellowstone Falls in Yellowstone National Park. And on the right side, we have the Grand Canyon and the Colorado River flowing through the Grand Canyon in Grand Canyon National Park. I don't know why I put Wyoming, it's in Arizona. So if we talk about the work of streams, we'll just talk about erosion and transport and then deposition. It's kind of our task for this little mini lecture. So as you know, if you've ever seen water flowing in a stream or a river, if it's flowing fast enough, it can carve out stuff pretty easily and it can erode pretty easily. Water's heavy and it has a very high erosive potential. So it has a lot of potential to kind of move material. So we just have this graphic playing through of some stream erosion occurring here in a field. And then this is my husband for scale, but this is the apartment I used to live in when I was in grad school at Virginia Tech down in Virginia. And when I moved into this apartment, this stream here did not exist. But over the span of 3 years, basically every time there was a flood or a big enough rain event, water would just start carving out this channel. And then eventually it carved out this full-fledged stream. And this channel, if my husband had stepped into it, was basically like 5 to 6 feet deep at this point. And that was just after 3 years of storm events happening. So water can carve out channels really, really quickly because of how erosive and how heavy it is. So just to give an example, let's watch a flash flood. So this is from Utah on September 9th, 2013. So we have kind of the stream channel. And then what this video shows is basically that as you have, let me speed it up. So I'll speed it up a little bit, so keep that in mind. So as you have sorry, why did I even do that? So as you have a kind of desert environment, if it can't soak in the water, basically you can have these flash floods that occur and then water can start eroding away an area quite quickly. So we have the arrival of this flash flood here, fast moving water. It's muddy because it's carrying a lot of debris and material with it as it has carved away areas upstream of this particular location where this person is recording this video. All right, so water's pretty erosive and it can arrive quickly, erode quickly, do a lot of damage through its erosive power. Okay, so when we're talking about water, water carries different materials. So in the video that I was just showing you, it is muddy because it's carrying certain amounts of what we call suspended material in it. So the total material that a stream is carrying, we call that its load. And a load is broken into 3 parts. So it's got a suspended load, a bed load, and then a dissolved load. So bed load is basically just stuff that kind of rolls or slides on the bottom. Usually it's like larger pebbles or boulders. If the water's moving fast enough, it might make them bounce, roll, or slide. So we call that bed load. And typically it's just either boulders or gravel that are on the bottom. And then we can also have what's called suspended load. So suspended load is stuff that's floating in the water. So a suspended load is usually made of silt and mud or clay. And if you have a high suspended load in a river, it's going to look murky, it's going to look muddy because you have a lot of stuff, silt and mud floating in that river channel. So it's going to look muddy like this image in the middle or murky like this image on the right side here. Lastly, you have dissolved load. Dissolved load is usually considered what we call salt. So it's things like sodium and chloride dissolved in water, so you can't actually see it, but it's also another contribution to stream load. So stream load is the combination of all 3 of those: bed load, suspended load, and dissolved load. All right, so for your first quiz question, you're going to look at the data in the table below. You have discharge, which we talked about in the last lecture, and then sediment concentrations in terms of milligrams per liter of water. So if you evaporated away water, a liter of water, it's telling you how many grams or milligrams of mud you would have left behind. That's your sediment concentration. So what you need to do is visualize what the plot would look like if you graphed it, or you can graph this data quickly, just make a little sketch, and then answer questions 1 and 2. Okay, so we talked about erosion, we talked about transport. Now we have to talk about deposition. So deposition is basically the act of a river stopping, carrying what it was carrying, and then it will form a pile or a deposit. So deposition can be any kind of material will deposit. Mud can deposit, pebbles can deposit, gravel can deposit, sand can deposit. So deposition just means that the water slows down enough that whatever it's carrying, it can't be held in the water anymore. And it settles down to the bottom and forms a pile. So we have 2 examples of some rivers here, and we have some kind of pebbly, gravelly material that's been deposited because the water's not flowing fast enough to pick it up and carry it any farther. So if we look at stream flow here, so we have just an animation that's showing us if you have stream flow or water flowing, it's showing you the material that is being carried. So as water is moving fast, it can carry larger material like gravel. And then as water starts to slow down and you have decreasing velocity or speed, then you get smaller stuff like sand. And then if water slows down enough, you will get things like mud. You'll get things like mud or clay that will drop out of the water last. So if I just pause this here, I'm so sorry. So if I just pause this here, the point is that if you have fast moving water, you get gravel and pebbles that will drop out first, and then it'll have smaller size stuff as the water slows down even more. Sand will now drop out because the water's not flowing fast enough to carry the sand. And then if it slows down enough, you're going to get silt or mud that will deposit farthest away from its original source. Okay, so you should be able to answer questions 3 through 6 on the quiz at this point, and then come back when you're ready. So when we're looking at deposits or deposition from streams, most material that a stream is carrying gets deposited on the floodplain. If you don't know what a floodplain is, basically if you have a regular river channel under normal conditions, a floodplain is the flat land that's adjacent to that river. And it's normally dry, but if you have a big enough flood condition or a big enough rain event, then water spills out onto the flat land adjacent to the river onto the floodplain. So if you watch this animation here on the bottom, if it rains enough, basically water spills out, goes over top of the bank of the river, spills out onto the floodplain. And usually that's where a lot of deposition occurs and carries nutrients with it. So that's why a lot of early agricultural societies were dependent, or civilizations were dependent on rivers for agriculture. So if you have a river and it's a snaking, meandering river, what I want to point out is that the water in the river, as it goes around bends of the river, doesn't travel the same speed. So what these arrows on this diagram indicate to you is the fastest traveling water. And what you'll notice is that it's not always in the center of the channel. So if water is flowing here, the fastest flowing water is in the center of the channel. But as it kind of goes around this bend, the fastest flowing water is kind of in the outside of this bend here. So water kind of shoots off and then goes back. The fastest water is going to be in the center, shoots off around the outside of the bend. So the point here is that if you kind of drew a line across at location A here, what you'd notice is that the slowest moving water is on the left side of the channel. The fastest moving water is on the right side of the channel. So as this does this, what it will do is it kind of carves away and erodes on one side of this channel and then leads to deposits on the other side of the channel. So if you're having a hard time figuring out why the fastest speed is kind of around the bend, you can just imagine yourself being in a car and you take the curve too fast, like this one here, your body shoots off to the side. Water does the same thing if it's going around a bend. It's like a car taking a curve too fast. So the maximum velocity or the fastest speed of water is usually in the outside of a bend. Just to give you a visual of this, so if we have a meandering, snaking stream, the white arrow here is showing you the fastest flowing water. And if the fastest flowing water carves out and erodes material, what the river channel can do is kind of adjust a little bit. So it might actually change its shape in response to that fastest flowing water. So let's say it does that enough, and you have a river that has started eroding a bank over here. Every single time that you get a big storm event or you get a big flood, what it's going to do is it's going to keep eroding away that same bank over and over and over again. So once it does that, it's going to start readjusting its channel. And what you should notice is that from diagram 1 to diagram 2, the channel is getting more curvy and more snake-like as the river has carved away and eroded away that channel. So on the opposite side of where erosion is happening, you get deposition. So you get sand or you get gravel that will pile up. And the reason for that is because the water or the velocity of the water is slower in that part of the channel. So it piles up and you will get kind of these what are called point bars. Here's a real life picture of what one looks like. So it'll have gravel and sand on it. That's where deposition occurs. And then on this side is where it's being cut into. We call that a cut bank. Here's a diagram that I drew with my mouse, so I apologize in advance in terms of what it looks like, just to kind of reiterate what I'm talking about. So these arrows here indicate the zone where water's flowing the fastest. So it doesn't take the same path as it goes through all of the bends of the river. If you are on the outside of a bend here, that's what we call a cut bank. So the water's moving really fast, so erosion is going to be happening there. If you're on the opposite side, you have slow moving water, and my red scribbles here are supposed to indicate what we call a point bar. That's where deposits form over time. So in every bend of a river, you have one side that's eroding, one side that's depositing, one side that's depositing, one side that's eroding. So let's say you have a river and it keeps eroding and eroding and eroding more. So diagram 1 is kind of your original river flow. E here represents erosion. So every time you have a storm, if the water is flowing this way, it's going to erode and cut into this area here. So if you take this meander and the river cuts farther and farther in, eventually what will happen is that you'll have a flood that's going to cut off that bend altogether. Water will take the path of least resistance, it's going to cut straight through that bend. And if that breaks off or cuts off, it produces something called an oxbow lake, which is kind of a horseshoe-shaped lake that used to be a bend of a river, and now it's been detached from the river. So if you want to learn more or kind of reiterate this concept, here's a link to another YouTube video that you could watch that discusses meandering rivers and the features that I just talked about and why rivers curve. Just to show you an example of how quickly rivers can change course, this is the Ucayali River in Peru from 1985 to 2013. Basically, we're looking at aerial imagery, so snapshots from outer space looking down on this river. And if you look at this zone here of the river, what it shows you is how quickly a meander can cut off and form one of these oxbow lakes. So it'll rewind, it'll start again, play again. So if you watch here, as this meander changes, it gets closer and closer together, then it takes the path of least resistance, and now you have this oxbow lake that has been cut off due to the action of this river. Lastly, the last thing that we need to talk about in terms of deposition is a delta. So basically when a river meets the ocean, it creates a delta. So a delta is the mouth of a river. There are lots of different types of deltas. They can take on many different shapes depending on what a river is transporting and carrying. But as an example, here's the Mississippi River. And when the Mississippi River reaches the Gulf of Mexico, it forms a delta, which is outlined in the dashed line here. And usually whatever material it's carrying with it, it's going to deposit. So you get lots of sand deposits, you get beaches and things like that. So you have the delta at the river mouth. Here's another example of a delta. So we have this Horton River here. It's flowing out towards a bay. And then you have the kind of this fan-shaped delta that is formed. All of this is just sand that the river was carrying. Fast-moving river met slow-moving water in the bay. And now you get this deposit of sand in a delta. All right, so at this point, you should be able to answer the remaining quiz questions, and then you'll have a third lecture for streams to watch as well.